It's my pleasure to introduce the first speaker of this conference, Professor Tomislav Pukšec. Tomislav is an associate professor at the Department of Energy, Power, Engineering and Environment, Faculty of Mechanical Engineering and Naval Architecture, University of Zagreb. He's engaged in research in the field of energy planning, sustainable development, modeling of energy consumption and systems, energy efficiency, and renewable energy sources. He participated in the organization of SDEWES conference, and he's a member of the local organizing team since 2011. Tomislav, it's my pleasure to welcome you.
Oh, okay. Thank you, Felipe, for this kind introduction. I'm very happy to be here today, of course, and to be able to talk about district cooling. I suppose a lot of you here are very much familiar with district heating systems. District heating systems are a major research topic on SDEWES conferences for decades now, with a lot of research papers, real implementation projects around the world, mostly in Europe. But when it comes to district cooling, we can stress out that there's not so many research out there in comparison to district heating. Of course, there are different kind of district cooling projects implemented around the world, but not so much in comparison to district heating. So in that regard, since we are in Morocco, I thought district cooling might be a very interesting topic to talk about. Especially district cooling systems are usually implemented in parts of the world with very hot climate, like the Middle East, or hot climate and very high humidity, like certain parts of Asia. So having district cooling as a topic seemed quite appropriate for today. I just want to mention or stress out that today I'm not going to go into very technical details of the district cooling systems, although of course we are going to mention some of them because we need them. But I will try to focus on smart energy systems, and I will try to see how can district cooling systems, how can they fit into a smart energy systems concept. So at the very beginning, smart energy systems, let's have a short brief. I mean, if I would have to choose one word to describe it, I would probably use the word integration. So thermal energy or thermal grids, electricity grids, transportation, heating, we all want to plan them and operate them in order to have this integratory factor. Why? Because we want to exploit certain synergies. Combining those systems will allow us. So flexibility of the supply side, integration of renewable energy sources, and subsequently decarbonizing our energy supply, whether it's electricity or heat. So having that in mind, we are always looking for, I would say, additional demand streams that we can integrate into the smart energy system concepts. Why? Because it will allow us a higher flexibility, and it will increase the flexibility and synergies, and it will allow us a higher, at the end, intake of renewables. With higher integration, we need different kind of technologies, different kind of policies in order to speed this process even more. When I say technologies, if we think about district cooling, those will definitely be different kind of thermal storage options. If we talk about advanced policies, then we definitely think about some kind of advanced market schemes or advanced market conditions. So where can we fit district cooling into district heating systems? Well, I would say right off the bat, we can stress out a few very important benefits or critical advantages of district cooling systems. So right at the beginning, we can say we can maximize operational efficiencies. Of course, how? Because we access multiple cooling sources. On the other hand, we are utilizing simultaneity of demands. which you cannot do on an individual building level. So actually utilizing simultaneity of demands will allow you to decrease the capacity of the overall system. On an individual building level, you can't do that because you have to satisfy the maximum cooling load, and there's no option, although you can have certain storage option on a building level. So what we want to do, we are actually trying to detach demand from the production. Another huge benefit of district cooling systems will, of course, be the reduced electrical loads, which is a very important thing. Actually, we want to detach electricity peak loads with cooling demand. They are quite correlated. Then we actually want to utilize different kind of storage options. For instance, aquifer thermal energy storage. It will allow us to, for instance, decrease our cooling peaks and have a much efficient system. We can utilize different kind of free cooling options. But here, when it comes to free cooling, I would say that we are utilizing, of course, different kind of heat-driven cooling units. And we are actually trying to connect district heating and district cooling in a co-production by utilizing vast amount of, let's say, heat pumps, which will later on allow us to have much better, much affordable heating or cooling tariffs. So one of the most interesting things, or one of the biggest debates when we talk about district cooling, and one of the first things people ask, oh, what is the difference or what is the benefit of district cooling in comparison to individual cooling systems? And this is one of the biggest topic when we are talking about this kind of systems. Well, we already mentioned we have a great reduction in peak power demand. And this is one cool example. On the right, you have one commercial building, Cleveland, US, around 30,000 square meters. You can see the comparison 2 years in a row. On the second year, they're actually discharging or discontinuing 2 electric compression chillers, and they are switching to district cooling. And you can see basically the effect of this process. District cooling is much more resilient technology. It can much quickly adapt to fuel prices, and it's more resilient from that perspective. You can stress out that different kind of storage options can be done on the individual level. So, for instance, on a figure here, you can see integrating ice bank on a commercial building level, and you basically have the same effect of smoothing out the peak electricity demands. But unfortunately, doing it on a building level is actually much more expensive. So doing this kind of demand side management and storing options on a system level is much more cost and technologically more effective. Euroheat and Power, I suppose some of you that work in district heating or cooling probably heard about them. They had a big policy paper where actually they calculated that utilizing district cooling in Europe in the long run can reduce the need for around 50 gigawatt of electrical capacity, and it accounts to around 30 billion euros in capacity and infrastructure needed for this process. And what they calculated is that with this 30 billion euros, you can actually cover almost 50% of the cost of this new district cooling systems that could replace them. When it comes to district cooling, usually district cooling systems are used for buildings, commercial buildings, public buildings, hospitals, data centers, industry, and so on. Not so much on classical residential building. This is a very nice research and a nice example where it's actually modeled or calculated for low-rise residential building with 3 different kind of setups. So RTU setup, so rooftop units, VRFs, so variable refrigerant flow, and district cooling systems. And the authors wanted to calculate all the constraints regarding economic, technical, environmental, and so on. And right off the bat, you can see from the results that a significant decrease in the electricity peak demand can be expected around 50%. But not just the decrease of electricity peak demand, a significant decrease in the electricity consumption as well, with, of course, significant decrease in environmental loading in regards of CO2 emissions. Another thing here worth mentioning is that within this research, a life cycle cost analysis was actually done for the period of 24 years, and it's actually shown that district cooling systems in the life cycle cost analysis shows to be much more economically viable than individual units and systems. The difference was around, let's say, 22 billion for RTUs, 20 billion for VRFs, and 17 for district cooling system, which is a significant decrease in economic parameters. So at the beginning, maybe I should have started with this, but let's just see district cooling systems, the basics. So we can define it as a centralized infrastructure. We are producing some kind of, in this case, chilled water, and we distribute it to different consumers in the system. Some of the main benefits we already mentioned: increased efficiency, increased flexibility, especially in urban areas that have a high density or the high need for cooling energy. So when we talk about the main challenges, of course, we want to meet comfort and process cooling needs. We are constrained with capital and operating costs, and reliability and flexibility and different kind of environmental loading. So in what way does district cooling alleviate those concerns for building owners or industry owners? So on one side, you can right away identify economy of scale. It allows you lower costs both from CapEx and OpEx parts, and it allows you a better reliability regarding equipment. As a result of that, you will have, of course, a longer lifetime of the equipment, which will increase the economic profitability. Of course, decrease in the consumption and electricity and cooling loads. And one quite important factor that we need to stress out here is actually the environmental benefits of this type of systems, because from the individual technology level, you will very often have different kind of refrigerant losses, which are quite problematic from the environmental point of view, while on the system level, you will be able to maintain and to regulate and to monitor this type of losses in a much better way. So to conclude this part, we have units that are used to produce cooled energy: chillers, heat pumps, and so on. We have different kind of storage options in order to match the coal production and coal demand curves. We also need a network to bring the cold energy to the final consumers, and to minimize the distribution losses in this regard. We are using different kind of variable speed pumps to deliver minimal differential pressure necessary to operate the building's ETS, energy transfer stations in this case. And of course, we do need different kind of energy transfer stations in this type of setup. We will show later on we have possibilities for other types of setups in district cooling systems, but this is the traditional one. We need ETS to adopt operating parameters to the building regime, like temperature, and pressure and flow and so on. I suppose if you are more into district heating, then at 2014 or 15, I think there was a very famous paper of SDEWES ISC members, and in that paper they were trying to categorize district heating systems into generations in order to have some kind of common framework and terminology on the technology, temperature regimes, and so on. Well, similarly to that, the same group of authors with the 10 years delay, I think in 22 or 23, they had the same paper where they tried to categorize district cooling systems into different categories. So I will just go briefly for you to understand how these systems evolve over time. So the first generation district cooling systems, actually, believe it or not, started end of the 19th century in the US. And the system was very simple. The distribution fluid was actually the refrigerant, and you had different kind of evaporators that were distributed around the city. And you had usually centralized condensers. The main purpose of this type of systems was actually food network supply, so different kind of warehouses that need refrigeration for food storage. And then in the second generation, around 1960s, we have a huge advancement in a way that the distribution fluid becomes chilled water. The main customers become usually public buildings, commercial buildings. And we are actually implementing compression chillers as the main technology to produce cold energy. Then in the third generation district heating systems, there's advancements in the integration part and new technology regarding coal production. So now with compression chillers, we have absorption chillers. We are using even heat pumps, and we are integrating different kind of storage technologies, and we are integrating slowly different kind of natural cooling technologies like lakes, rivers, sea, and so on. So this is third generation is like 1990s. And then we get to the fourth generation district heating, which we are now, 2000s, 2010s. And here, the main drive in the fourth generation district cooling systems is actually the overall need for decarbonization. This means that CHP slowly, especially combustible fuel, slowly starting to be left out. And I would say that overall property of the fourth generation district cooling system would be the integration with electricity, but also integration with district heating. So this is the one of the main components of these new systems. So focus is on exploiting both ends of the heat pumps simultaneously. In the fourth generation district heating, the key issue is that you have the heating demand and cooling demand at the same time. Of course, you can have a separate chiller and heat pump working in parallel. So using heat surpluses obtained from cooling for covering different kind of heating demands, and surpluses called from heating can come and satisfy certain parts of the cooling demands. So one of the key technologies here is actually utilizing different kind of natural cooling, or we call it free cooling. So basically, if you look at district cooling systems around the world, they are usually next to the sea, river, lake. And the idea is to utilize this energy as free cooling energy, especially if it's cold enough. So in this case, in this scheme, in this figure, this is currently a synergy between free cooling and compression chillers, but you can actually bypass and go directly to heat exchanger and use this energy in parts of the year when the energy or the temperature of the free cooling source is low enough. In Helsinki, for instance, 6 months of the year, so 6 months per year, they're actually using free cooling, and 1/3 of their cooling demand is actually covered by free cooling, which is an excellent result. Another key component in the district cooling systems are, of course, chillers and the integration of chillers, especially in the second and the third generation. The third generation absorption chillers became very important because it allows us to utilize different kind of waste heat streams. In general, the size and the number of the chillers will depend on various conditions. So from purely commercial availability to some maximum and minimum loads in the network. On the compression chillers, important component is also the possibility of heat recovery, which allows us to use the technology both in the heating and in the cooling process. So another important issue, as I mentioned, fourth-generation district cooling systems are all about decarbonization and all about integration with electricity and district heating. So the key component here is integrating renewables into those systems. We can look at it from two points of view. We can look at it from thermal point of view, or we can look at it from the electricity point of view. From thermal point of view, there are numerous renewable energy sources that can be integrated into the system. We usually need some kind of absorption chiller technology in order to do that. So for instance, if we talk about geothermal, but also we can utilize waste heat from geothermal power plants if there's availability. We can also consider here groundwater source heat pumps as one of the technologies. When it comes to biomass, solar thermal, waste heat, we usually utilize it through different kind of absorption chiller technologies. On the thermal side, we can also say that the different forms of free cooling could come into the same category. On the other side, we have district cooling coupling with electricity sector, which is the most important part of the fourth generation. But in this case, the decarbonization of district cooling will be very much affected by the decarbonization of the electricity sector. But decarbonization of electricity sector is very much on the way. So in the long run, heavily electrifying district cooling will basically means heavily decarbonization. Final maybe things to mention here, the combined heating and cooling and power technology. We will discuss it a little bit later on. This is a very cool example of district cooling system integrating solar energy, both solar thermal and PV. A cool thing about solar and cooling is that the solar demands or solar radiation curves and cooling demands very much correlate, which creates a certain synergy between those two systems. In this case, it's a very good example on the integration of PV and solar thermal together with hot water tank, chilled water tank, and classical compression chillers, and we can see the benefits of those synergies. Finally, one of the key issues or key benefits of having a centralized system is actually being able to do the maintenance and regulation much better from the system point of view in comparison to individual technologies. So centralized equipment monitoring, SCADA. So you have different kind of sensors continually measuring critical parameters and enabling, based on this real data information, you can create different kind of strategies for running the compressors, to regulating the networks, and so on and so forth. Predictive maintenance technologies also is very important from the system point of view because it can predict equipment failure before it happens. So in that regard, you will have much less downtime than individual technologies. And purely, if we talk about efficient use of maintenance resources, economy of scale, you will always get much better economic deals for spare parts and so on if you do it on a system level. We can check very quickly how like a traditional chiller plant maintenance operation looks like. So you have a very detailedly defined the parts, the technologies, the time frames, the necessary procedures for each step of the way, which is very efficient in the long run. Okay, when we talk about smart energy systems and district cooling in smart energy systems, we should probably start from the network. We have quite a big difference between district heating and district cooling networks. I mean, the biggest difference is the smaller temperature difference, which means you need bigger dimensions or bigger diameters of pipes, which subsequently will increase the price or the investment price. And this is the reason why actually when you compare district heating and district cooling, when you compare their networks, district cooling networks are much shorter than district heating networks. And this is one of the main reasons for that. So for instance, if you have DN 400 pipe, you can push around 15 megawatts capacity in district cooling for 6 degrees Celsius, 3.5 meters per second flow. And in the same DN 400 pipes, you can push 70 megawatts of capacity in district heating, 30 degrees Celsius, with the same flow of, let's say, 3.5 meters per second. So it's a big difference. And in order to increase the efficiency in district cooling systems, you will very often see district cooling systems clustering around areas of the city which have a huge cooling demand. And it's not very unusual to have additional production units around the network and actually connecting these parts and clustering these parts into a single system. This is one example that Danfoss is doing. Danfoss is doing in Denmark. On the regards for fourth generation district heating systems or district cooling systems, one of the key components is actually the bidirectional energy exchange. And in order to be able to do that, we need something called BLTN or bidirectional low temperature networks. So heating and cooling consumers are basically connected to the same network. You have a warm pipe and you have a cold pipe. The temperature difference is around 10 degrees Celsius. Temperatures are close to the surrounding temperatures, let's say 5 to 30 degrees Celsius. As a result of that, you will have less thermal losses. So the idea behind this bidirectional energy exchange is actually you raise the temperature for heating or hot water by using heat pumps that use warm pipe as a heat source. Cold water from the evaporator is discharged to the cold pipe. Vice versa, chillers use network as a heat sink, basically. They use the water from the cold pipe and discharge the heated fluid into the warm pipe. Here, the key thing is that we have to have simultaneously for heating and cooling. And we are doing a whole different shift. We are switching from traditional system where we have a district cooling or district heating, where we have final users, which are consumers. But in this case, the final users are actually becoming also producers, which means we are coming to the state where we have prosumers in the heating and cooling supply. Another important benefit of this type of systems is that it actually allows us to integrate very low temperature waste heat from urban heat sources. So waste heat from supermarket refrigerators, waste heat from electrical power substations, and so on and so forth. And since we're here on this slide, maybe one additional explanation from a terminology point of view. If you go into literature, very often you will find bidirectional energy exchange systems as 5th generation district heating and cooling systems. In the classification I showed from our colleagues from Aalborg, they are actually dividing the 4th generation district heating and cooling systems into 2 types. So the centralized 4th generation district cooling system, which means you have separate network infrastructure for district heating and separate network infrastructure for district cooling, or what they call it 4th generation district or decentralized 4th generation district cooling system, which basically uses one thermal network, which is quite close to the regimes of the district cooling network. And in this case, we usually are much more benefited if the cooling demand is higher than the heating demand. So just to clarify, I'm not going to give any kind of position on which terminology is better. I'm just saying that you will probably find different names in the literature if you go and do the research. One of the key thing and one of the biggest issue on efficiency of BLTN networks depends, as I said, on the simultaneity of cooling and heating demands. We call it DOC, or demand overlap coefficient. So it can be from DOC 0, which means there's no overlap, and it can go to DOC 1, which means there's an excellent overlap. What is important to stress out here, that higher demand overlap coefficient, the better the system COP will be. And if you look at the figure below, this R coefficient, I don't have a pointer, so unfortunately I can't point it out, but this R coefficient is actually the ratio or share of the R is the share between heating demand and cooling demand. So if you look at the upper green levels, those are COP and economic variables for 4th generation district heating system, which has a higher cooling demand than a heating demand. So this is a very important parameter when discussing this bidirectional energy exchange networks. Another important thing we need to mention when we talk about district cooling systems is their possibility on demand side management operations. So from peak clipping, valley filling, load shifting, strategic conservation, strategic load growth. It's important to stress out that this DSM management is not only part of the plant or district cooling plant, it's actually a part of a greater smart energy system concept. And this DSM or load management connects to all the subsystems connected to the district cooling network. There are numerous direct benefits, indirect benefits we can stress out. From different kind of financial benefits for the final consumers, the much wider market benefits in a way of lowering wholesale prices, increasing reliability, and various indirect benefits connected to less environment constraints, additional market development, and so on and so forth. When it comes to peak shaving, the main technology that we use in these systems would be some kind of cold thermal energy storage. So during summer, peaks in the electricity demand usually occur when the cooling load is quite big. The difference between heating and cooling is actually the cooling demand can vary more during the day. It can be quite dependent on the solar curve. So for this case, we actually use different kind of thermal storage options. There are some drawbacks when it comes to thermal storage options. So we have increased costs, and the costs in general can be quite high. You need some kind of dedicated space for this cooling or storage options. Thermal losses can be substantial, especially if you talk about long-term storages. And the design and connection planning can be quite significant. In this example, this is actually a good example of utilizing storage, thermal energy storage, by utilizing much more favorable night tariffs for electricity. So if you look at the numbers, basically the electricity consumption is more or less the same with or without thermal energy storage, but the overall price is almost half lower because you are actually switching production from day to night. So if you look at it a little bit wider, then I would say this is an integration of wind and district cooling, because during the night we usually have wind power that needs to be utilized. I didn't actually want to go to cogeneration and three generation because I don't think that they are or will be a major part of the fourth generation district cooling systems. But I decided just to mention it, just to have it as a technology still being used in certain second and third generation district cooling systems. Of course, when it comes to cogeneration, you have this gap between summer and winter in heat production, and you need to find different kind of ways to utilize that heat. And upgrading cogeneration to a three generation plant, it's something that increases the efficiency of this type of systems. The fault of these systems, or the negative side of these systems, is usually in the cogeneration plants we use fossil fuels like fossil gas. But from renewable point of view, we can discuss for future cogeneration plants running on renewables from biomass, biogas, any kind of synthetic fuels and so on. So in order for cogeneration or three generation plants to be viable as a part of some future district heating and cooling systems, this step will probably be very much necessary. Well, I mean, when it comes to regulation, optimization of the system, in today's systems, in fourth generation district heating systems or district cooling systems, Internet of Things, AI are a major part of that. So you have different kind of IoT-enabled real-time monitoring, so temperature, flow rates, energy consumptions, and you can precisely control the chillers, you can precisely control the network, which increases the efficiency. You have different kind of enhanced peak shaving with AI, so different kind of AI algorithms can predict cooling demands and simultaneously do different kind of demand side management. Also, AI can do different kind of peak demand, including different kind of meteorological data and connecting and optimizing thermal storages in order to shave those peak demands. EU is quite clear on the position of district cooling systems regarding their energy and environmental parameters, because European Union sees district cooling as a part of efficient district cooling and heating systems. One policy that I would mention here that will make a major change regarding district heating and cooling is the recast of Energy Efficiency Directive, where now EU countries will need to develop local heating and cooling plants, and all of them that are above 45,000 people. So it's going to be, I think, a new push towards more efficient cooling systems. Okay, let's look at some cool examples of district cooling systems around the world. There's a lot of them. We'll go through some of them, and I've chosen a few specific ones, each of them having some very specific added value that I wanted to discuss. So the first one is Stockholm district cooling system as a part of sustainable urban infrastructure. Probably one of the largest ice storage chill water systems. 400 buildings, around 250 kilometers of network. So integration with district heating, using cold supply from large heat pumps provided providing heat to district heating. Largest heat pumps actually use district heating and district cooling from purified wastewater. It's one of the biggest systems, around 220 megawatts, around seven big heat pumps. Here, the cold storage is actually a cavern, which is a very interesting technology. Paris is another interesting example. Coal network of Paris, around 700 customers. In the 10-year time, they will reach around 160 kilometers of network. Here, it's a combination of compression chillers and free cooling. They use River Seine for their free cooling purposes. And they have different kind of storage technologies, around 140 megawatt hours per day. In Paris, it's actually it's cool. They have a cold storage, ice storage, around 90 megawatt hours per day. And it's interesting how they operate it. They actually even fill the system and the storage during the week, when there's not such a weekend, when there's not such a big need for the cooling energy. But actually, in this case, they're using the network as a cooling storage, because the network is around 8,000 cubic meters, which also increases the efficiency of the system. Helsinki, also very interesting example. They're integrating free cooling. As I said, almost 6 months a year, they're using free cooling, and it's around 1/3 of the all cooled energy. They have a lot of waste heat, so they use a lot of absorption chillers. They have waste heat from industry. They have waste heat from electricity producers, but they also integrate heat pumps which produce both for district heating and district cooling. In Helsinki, for instance, COP is around 5, which is a very good numbers. Basically, Helsinki produces 80% of the production. 80% of the produced cooled energy is actually produced from resource that would otherwise be wasted, which is a very sustainable way to run the system. Copenhagen is also a very interesting example. Seawater cooling as well. In winter, it's around 6 degrees Celsius. During summer, they use compression chillers. Here, it's very important when we discuss district cooling system, as one of the key components is in what percentage do we have different types of customers or consumers. So, for instance, in Copenhagen, around 50% of the consumers are actually, they need comfort cool. Around 40% are for process cooling, so industry, and then around 10% are for freezing cooling. Copenhagen is also a good example. I always give it because it's one of the best examples how advanced optimization strategies can increase the efficiency of the system. This is done by Danfoss. This is not a commercial, but it's an excellent example how very advanced regulating and optimization technologies can bring benefits. In Copenhagen, COP is around 7. Of course, we can't talk about district cooling systems without mentioning Dubai, the largest system in the world. Total capacity around 5.5 gigawatts, 88 cooling plants, almost 1,600 buildings. Extremely efficient system with most advanced operating and regulating tools, integrating PVs, thermal energy, reverse osmosis, and so on. But here I would stress out one other thing. Here it's very interesting how national policy can influence different kind of technology options and strategies. So in the case of Dubai, the national government had a national energy policy, and in that national energy policy, they said our strategic goal is to decrease electricity peak demands, and please do something to do it. And district cooling system was one of the best options to actually do that. And with the integration of district cooling in Dubai, actually they have lowered the peak load demand for electricity for around 40%. So this is a very good example how a very strategic national policy can define certain technology pathways. Singapore Marina Bay is also a very interesting example. I'm giving it here because it's a very good example on how to utilize shared infrastructure. If you have district heating, if you have district cooling, if you have electricity, if you have IT cables, and each of those digs their own pipes and puts their own network, it's a catastrophe, it's a mess, and it's very expensive. In Singapore, they have something called multifunctional common service tunnel, which is like a network corridor throughout the city, which is used to lay different types of infrastructure in that. And district cooling system in Singapore is actually using this multifunctional common service tunnel. It's an excellent way to save costs, avoid redundancy, and to use this shared infrastructure to have a much sustainable solution. Toronto is also a nice example of district cooling systems integrating, in this case, with water supply. So Toronto takes the water from Lake Ontario, around 5 kilometers out of shore at 80 meters depth. And they have huge pumps. They bring the water to shore. And first they treat the water because they will use this water as a drinkable water. And after they treat the water to be drinkable, they use this water in the district cooling process because the water is around 6 degrees Celsius. So they use the water in the district cooling process. And they use part of that free energy in their district cooling. So it's also a nice synergy how two different systems can correlate and save costs, because you would also need to take the water out for drinkable water, but you're else actually using part of the energy here as well. Chicago is also a very interesting example. Probably the largest ice storage chilled water system in the US. It uses ice storage units, and it works pretty similar like Paris. So during the night, they're utilizing the cheaper electricity in order to produce ice, and they're melting the ice during the day to reduce the peak cooling demands. Here, it's also a very good example on how they're actually utilizing, they're saving fresh water by utilizing Chicago River to be used in cooling towers, and in that way, they're saving a certain amount of fresh water. So, lessons learned. If we talk about after we went through all of these systems, we can say that environmental impacts and decarbonization is becoming a crucial thing. District cooling systems with heavy electrification and using different kind of renewables, free cooling technologies, and so on, are perfectly in line in this process. The key issue is integration, but not just energy integration, but much wider integration, as we saw, integrating desalination, integrating water supply, and so on. Like all distribution energy systems, district cooling has a high cost to it, but in the long run, it actually proves to be economically more viable than individual solutions. And there are actually numerous benefits of district cooling that are not purely energy related. So, for instance, one of very important benefits of district cooling is actually reducing urban heat islands. What are urban heat islands? So basically, urban heat island are all urban areas that have a significantly higher temperature than other surrounding rural areas. So asphalt, concrete, cars, different kind of equipment, and air conditioning units will all bring and intensify this heat island effect. Of course, district cooling will not alleviate heat island effect alone without any kind of advanced policies regarding green infrastructure, water surfaces, and so on. But it will significantly decrease heat island problems, because reducing ambient temperature is very important, because you're actually increasing the quality of life in these urban areas if you alleviate that. Another big example of, I would say, indirect benefits of district cooling systems is actually optimization of infrastructure and saving space. So if you take down all the chillers, all the cooling towers, all the AC equipment, it's much better from optimization point of view, or from a space optimization point of view. And it actually, if you are taking it down, you're also reducing buildings' structural load, which is also a very important thing. Okay, maybe to summarize. So when it comes to optimization of infrastructure and space, so we said shared infrastructure. It's very good if you have the possibility of common shared infrastructure pathways. Then you will consequently increase land value and usability, because safe space can be utilized for far more valuable activities. Buried pipes, free surface level. Without these constraints, actually, without these constraints passed by mechanical equipment related to air conditioning, architects and urban planners can gain more freedom in the designing visually appealing buildings, more sustainable urban spaces, and so on. One example I would also mention here, since SDEWES started in Dubrovnik, and it comes back to Dubrovnik this year as well. I just wanted to share this one cool example where district cooling systems can be integrated into very specific requirements. So you have a very old city like Dubrovnik, which is UNESCO World Heritage City, but it has certain problems. The problems relate to AC units in the old city. So you have historically very important building that you are visually, I'm not saying they are ugly with AC units, but they are not so visually appealing with them. You have, of course, heat island effect, because it's stone streets, very narrow, and if you have a lot of AC units, you're actually discharging this heat into the environment, which creates and increases the temperature. And another issue, at least that I mind a lot, is the condensation and the condensate issue that is usually being discharged on the street, which makes the streets slippery and so on. This type of old cities in Europe and Mediterranean, there are a lot of them. So for them, district cooling system is a very interesting and viable option. The city of Dubrovnik actually had a very nice feasibility study where they tried to construct the system for district cooling. Unfortunately, they didn't succeed yet, but hopefully at some point they might do that. And final slide. I just wanted to look at the market share and the future potential of district cooling systems in the world. So International Energy Agency World Energy Outlook in 2024 says, or it projects, space cooling demand increase on average by 3.7% annually till 2035. 90% of that will come from emerging or developing countries, from rising standards, population growth, and climate change, because the temperatures are getting higher. For developing countries, the projection is around 200 to 280% increase in cooling demand till 2050. In Western countries, not so much. If you look at US and if you look at Japan, the saturation for cooling is quite high. But in Europe, it's actually quite low. So I would expect in Europe as well a certain decrease in the cooling demand. And in that regard, district cooling systems pose themselves as one of the key technology, especially because they alleviate a certain issue regarding electricity peak demands. Danfoss has an outlook and has a projected district cooling market growth. And based on their projections till 2023, we actually expect the district cooling systems, I think this is for Europe, that should double, more than double in the next 10 years. Okay, thank you. Thank you very much for your attention. If you have a question, I would be happy to answer.
Thank you. Is this on? Yes. Can you hear me? Yes. Thank you, Tomislav. I would like to start with a question or two.
Sure.
First of all, what will be the main barriers that you see for the deployment of district cooling?
The main barriers, well, I would I would define them as technical and non-technical. And they would be very much dependent on the region of Europe or region of the world where we are applying them. But technical barriers, I mean, district cooling as district heating, it's a centralized system. So at the very beginning, you have a problem of high capex at the beginning of the project because it's a shared infrastructure. And in that regard, this increase in investment costs needs to be shared somehow. Is it going to be some kind of a communal activity on the city level, or is it going to be privatized? It's different kind of strategies that can be implemented, but I would see this as one of the barriers because at the end, you know, putting an AC on a building, it's much easier than connecting to a DC system. From the technical point of view, I think in the fourth generation or third generation district cooling systems, from technical point of view, I think we are very much advanced, and I don't see any huge barriers here. I see more this sociological and political barriers that correlate with these technical ones. On the non-technical side, as I said, these barriers can differ depending on the region you are talking. So, for instance, for Southern Europe, this shared communal infrastructure is a little bit problematic from socio-economic or socio-political point of view in comparison to Nordic people, because for Nordic people, it's perfectly normal to have a district cooling or district heating network. They are all okay with that, but on Southern European mind, this individualization is maybe more stressed out. So here you will need different kind of advanced policies, I would say, that could try to alleviate this socio-political element. Yeah.
Thank you, Tomislav. One more question before opening the mic to the public. You show some really nice examples of cities that have basically implemented district cooling. But most of those cities were, you know, like big cities from big countries. Where do you see new markets or new opportunities for district cooling that, you know, differ from what you basically showed?
Believe it or not, this morning when I woke up, I turned out my TV and there was like, it wasn't CNN, but it was some kind of news channel. I'm not sure which one was it. It was actually a report from India, and the report was on AC units in India, how they are treated as valuable, and how the dream of regular population is to actually have an AC. So cooling will be very problematic in developing countries due to, as I said, increase of population, economic growth, so people will have more economic funds and they will want to afford cooling solutions. And of course, climate change and increase of temperature is one of the reasons. So I see the biggest potential for district cooling actually in those type of markets. As I said, district cooling is quite different in comparison to district heating because you can't have huge systems, kilometers and kilometers of networks. So usually district cooling systems are smaller. So in that regard, if you have an area with very dense heating demand, whether it's Accra or I don't know, New Delhi or whatever, it's a very very feasible way to satisfy cooling demands. To be fair, this high cooling demand or density of the cooling demand is probably on a massive commercial or public building area, but even on massive residential buildings, because you have those in these countries. So I would say those are the main markets. But I also see Europe as a potential market for district cooling, because as I said, Europe, in comparison to US and Japan, still has quite a low saturation for cooling. And also with this climate change, increasing in temperatures, which we see every day in Europe, cooling solutions will be needed, and advanced cooling solutions that can be optimized, regulated, integrated into much smarter energy systems will probably be placed. So I see Europe here as well as an important market. Yeah.
Thank you, Tomislav. Nevin?
How do you see architectural methods to decrease cooling demand? For example, double skin facades or traditional architecture. Moroccan architecture is an example of that, or Northern Africa one with forms, less solar forcing, also air circulation inside the buildings. Or, for example, Caribbean architecture, which has a lot of airflow. Is it something that we should be pushing, or we should say everybody builds whatever they want and we satisfy the cooling demand?
Absolutely not. I would never allow anyone to build whatever they want. It's chaos and mayhem. So I would always stick to some kind of regulated activity, especially when it comes to buildings and building buildings. From my perspective, from European perspective, I think when it comes to decreasing cooling demands on a building level, I think this is more or less clear. We have a very strict building codes that define how we need to build buildings, and one of the cornerstones of these building codes are actually what type of material can you use, what kind of isolation you need to put. So that technically it's more or less done. If you're building a new building, it's basically nearly zero energy building. You have architectural freedom to use different kind of architectural solutions. So you can position your building so it has a beautiful glass surfaces towards the sun, so decrease the heating demand during the winter, or have different kind of shading options to decrease the solar gains during the summer. So this is something that will continue to go on, especially now when you have new European Bauhaus as a European concept which integrates energy, environment, but also architectural solutions and so on. So I think here we are more or less defined. So I think in the future period we will significantly decrease the cooling demands with isolating buildings, because it's just the law, and there's not much to do here. For other types of the world, for other regions of the world, well, I'm a I wouldn't say traditionalist, but I can appreciate traditional architecture. So I would definitely be in favor of utilizing local specificness in order to increase overall efficiency. So any kind of local specificness in the Arabic architecture, which allows circulation, cooling of the air, or so on, it's more than welcome, I would say. I would maybe even structure it in some kind of a building code in order to do it properly if people really want to do it. Because if you don't define such things in building codes and you leave people to interpret themselves on what traditional is or how can it be done, then you get a lot of problematic cases in real life.
If I may, another question?
Yes, please. We have time for one or two more questions.
Okay. I was recently in a discussion with a researcher who told me that if you don't care about heat islands and aesthetics, and if you don't care about peak shaving and heat storage and things like that, but comparing local cooling with centralized cooling using air-to-air heat pumps, it's basically less efficient to have district cooling. And this is a position that is quite strongly entrenched in one of the biggest countries.
Show me the research and the calculation, and then I can comment.
Okay.
But, if it's just, I didn't see it. I didn't see any kind of comparison.
If you have COP3 at the central location and distribute it, then you have additional losses because you transport cold.
Okay.
Then you are having lower efficiencies. So you correctly mentioned all.
Thank you very much. Although it was a detailed question, that what is the you think what is the major challenge that facing the modern cooling and heating system, like the cost, for example, the user control, sustainability? What you think and why?
Well, I mean, there are numerous things you can stress out. I mean, we can talk about different kind of. One of the things in the cooling system in general is you're always trying to find refrigerants that have much less GWP potential in order to have the system more sustainable. So that's always a research question and a topic. You're always trying to increase the overall system efficiency by integrating different types of energy and storage options in order to have the overall efficiency much better. So those are probably the things that would be interesting from a district cooling perspective.
Thank you. We have a question in the back, please.
Yes, hello, Marko Keber from the University of Ljubljana in Slovenia. I'd like to follow on what Professor Dujic just said. So it's not just researchers that have noticed this, it's also the customers. So we're looking at the different heating and cooling systems in Slovenia, and the feedback that we get from the customers is that they want to disconnect from the systems because it's cheaper for them in that particular moment, not in the long run. So when we do the analysis, we see that in the long run, there might be several benefits, as you mentioned, but in the short, or when they have to pay, at that moment, they don't want to pay for the district heating or the district cooling, but they prefer to install heat pumps, AC units, and so on. So my question is, has there been an example of where district heating has been converted into district cooling? Why? Because we noticed in some parts of the country, people want to disconnect from district heating because they've maybe insulated their house, renovated everything, they've installed heat pumps, and they realize that they're more self-sufficient this way. But in the summer, they have to pay more, their costs increase because they have AC units. So has there been an example or a study that would say, well, how about converting district heating, keeping the customers, having district cooling instead?
Okay, first comment, just a comment on the first part of your question. Yeah, I mean, in Croatia, when it comes to district heating, we have similar cases, so it's not something that we didn't see. But in Croatia or in general in Eastern Bloc, I mean, district heating systems in the last, especially in Croatia, in the last forever, basically, are actually systems that nobody wants in a way that, you know, the national utility company operates them, but they actually don't want to operate them. The city government doesn't actually want to have anything to do with them. So systematically in the last decades, you're actually neglecting that systems. And in combination with the fact that customers didn't pay their actual consumption, but they were paying per square meter, killed any effort or any need for energy efficiency in those systems. So it's like in Croatia, when it comes to district heating, it's like historical legacy that is very problematic. And as a result of this historical legacy, the systems are not so efficient, quite old. They don't integrate different kind of advanced production or storage options like modern district heating systems in Germany, Austria, and so on. So we have this historical legacy problem, and it's very difficult to fix. They're trying to fix it. They're changing the system of payment to individualization of payment. They are integrating some storage technologies into district heating systems. They are renovating the networks and so on. So something is changing, but still we have these cases, as you mentioned, where people want to switch off. On the other issue, or on the other question you mentioned, to be honest, I don't remember a system that was district heating system and transferred to single district cooling system. I didn't find this, but there might be. I'm not saying they don't exist, but to be honest, I didn't find it.
Thank you.
Is there any other question? Go ahead, please. In the first row.
Yes, maybe in Vienna they used district heating for cooling purposes, so it's not switching, but additionally, yeah, this could be.
They are integrating district cooling with district heating.
Yeah, but not switching. Yeah, so you're right. Yeah. Okay, I just have a question. Maybe in developed countries, the majority of demand increase in electricity consumption will come from data centers and you know, servers, etc. So are those the places where could be the core of future district cooling systems? Because maybe there is then initiative that you make them cheaper and more reliable, and then with some let's say additional capacity, you could build the core for the cooling the wider regions. So what is your opinion on that?
I would fully agree. I think data centers are actually the cornerstones of future district heating and cooling systems, because the amount and the number that we will have to build in the forthcoming period will be a significant waste heat facility, but also a facility that needs a substantial amount of cooling. So I would definitely, in the developing world, building my systems around or close to data centers for sure. Yeah.
Is there any other question from the public?
Sorry for being
No, we have
18 minutes above.
we have 10 more minutes.
10 more minutes,
Yeah,
but
lunch is a bit late. So
lunch is a bit late. Okay.
Is there any other question? If not, I might have a couple of more questions for you, Tomislav. So let's go to markets. So you talk a lot about the engineering side, you know, the mechanical side, but at some point you mentioned prosumers.
Mhm.
So let's say we live in an energy community, and we have, you know, some members of that community with rooftop PV or something, but others not. And then when they have excess, they can, put their excess electricity, basically produced by the rooftop PV, into district cooling, and others might benefit from that, excess electricity. So how do you price or create tariff such that these, communities can actually be fair in the way they access the excess electricity put into this district cooling?
Well, I think in this case, the tariffs should be dynamic, and they should depend on certain specific variables in the systems, whether it's, sorry?
The mic.
Sorry. I would say that in this case, I would say the tariffs should also be some sort of dynamic and should be connected to certain network or energy parameter valid in the system itself. To be honest, there's not a lot of data on this, and it's a very interesting research topic, especially on advanced heating or cooling markets in this bidirectional energy systems. It's very interesting to see how to price certain energy flows because you're using different technologies with different efficiencies by producing heat and cold at the same time in the same system. So it would be very interesting to see how to structure these policies.
And I'm also thinking that maybe in some countries you might have net billing or net metering. So
of course.
You can actually choose if you send the electricity back to the grid or use your excess electricity to produce, basically store it as a heat or cooling, energy. So, that's basically what I'm thinking about. From the prosumer point of view, what would be more attractive?
The logic would be quite similar to electricity, I would say, with some specificness because heating and cooling is a little bit different game than electricity. But the logic would be quite. I mean, we did have some research on market pricing, but for heating. But integrating cooling into the equation it brings up or increases the complexity. So to be honest, this is something that's going to be some kind of future research focus, especially in these bidirectional networks. Yeah.
Any other question? On WhatsApp? So Sakib is asking, in the context of growing energy demand and climate change, do current heating and cooling technologies represent a sustainable long-term solution, or are we due to a fundamental shift in how we control indoor environments?
I'm not sure if I understood the question. Can you?
Yeah, in the context of growing energy demands and climate change,
Okay.
Do current heating and cooling technologies represent a sustainable long-term solution, or are we due to a fundamental shift in how we control indoor environments?
Well, I think they do. Basically, I mean, you can always debate systems being better, finding new solutions, finding new technologies, increasing efficiency. That's perfectly okay, and it should be done. But if we look at today's technologies, I would say they fit in this general framework, but only if we have a decarbonized electricity sector. Because we are using electricity in the heating and cooling solution. So if the electricity is renewable, then our heating and cooling solutions are renewable. So I would say yes, they fit the current framework, but that doesn't mean we should not investigate or research the current framework in order to find something better, because there's always something better out there, and that doesn't mean that we should not try to find it. But I would say they fit. Yeah.
So I have one final question, and with this we finished.
Yeah.
One more. If we want to support, or to really speed up the deployment of district cooling, from the government point of view, what are the regulations that are needed to speed up basically this process?
Well, first of all, you need to have a very good building codes in place. So that means that you have to be very strict in defining what can be built from energy consumption point of view. So you have to be very strict in defining, let's say maximum heating energy, useful heating energy per square meter. So if you're building a new house, it has to be less than 20 kilowatt hours per square meter. And this is like a prerequisite of everything. If you want to start building efficient systems, then the first step is actually to build buildings in a very efficient way, so they really consume a low amount of energy. And when you have that, then you can discuss different kind of technologies that will help you go from this useful to final level with different technologies, efficiencies, and so on. So from district cooling point of view, I think the key issue is this holistic synergy that you get on a system level. And you need to be sure how to valorize it and how not to create certain resistance from the final consumers. So you will never push district cooling system or district heating system in a rural area where you have low heat demand, buildings and so on. But if you have a very densely populated area with huge heating or cooling demand, like city centers and whatever, then you need to frame the building codes and urban zoning codes in a way that you give some kind of prioritization to this type of systems. Should it be done forcefully in a way you have to do it? Or should it be done through very fine-tuned taxation measures where you would taxate certain technology more than another in order to push people into another direction? I don't know. I don't have a clear position on this because both positions have positives and negatives. So I would say the first step is to make sure that the buildings you are building, the buildings you are renovating, you are doing it very efficiently, and that when you build them and you renovate them, they consume a low amount of energy. After you have that, then you build on the other side. These two processes can go simultaneously, don't get me wrong. So you don't have to wait for all the buildings to be very energy efficient and then start. In general, the process, how it should be done.
Plenary, thank you again. And we can go for lunch now.